Hello and welcome back to Old School Coding, where we are continuing work on the simulation of a 1990-ish microcomputer written in C99 using some of the tools and techniques from the late 80s and early 90s. So far we have completed a number of support chips and we have filled out most of the 8080. We've got all of its instructions going. Have not yet done anything with interrupts or the support for DMA, and we don't support wait states on writes to memory or I/O writes. So we're not done yet there. But now's the time to start filling out the rest of a potential system so that we can actually start interacting with it as we bring up more capabilities. So the next thing I want to do, as you have seen in the title, is I want to establish some character devices. So my options here were kind of limited. At the time, there were two potential ways of doing a serial device. Intel had some fairly difficult to use chips for doing serial and parallel work. They aren't that absolutely difficult, but on a relative term, they were more difficult to use than some of the simpler alternatives. And my favorite of all of the serial interface chips is what AMD came out with, the 8530, which was much superior to the Intel product at the time. We actually ran some comparisons. Sun settled on using this chip for their serial consoles. I ended up working on that driver. In fact, I owned that driver for several years. And consistently what we found was that if we had shifted over to the equivalent Intel product, the load on the CPU would have gone up and our performance would have gone down. The AMD products gave us some additional abilities. However, I've decided not to actually attempt to model a UART chip because in the end, what you get out the other end is you get a bit wiggling. And unless I want to make this simulation locked to real time and wiggle a wire in real time and then go chase down a terminal that plugs into RS-232, I think the better thing to simulate is to have a similar interface, okay, very similar in some ways, and then start stripping it down. The salient part of the 8530 that I really loved was it did have a silo internally, so it could receive more than one byte of data. So you didn't have to empty out its byte register before it could start receiving the next character. And I believe it had a silo of like 16 characters. And same thing on output. You could start feeding it data, and you could get a little bit ahead of it, and it would drain it, while you went off and did other things. So the centerpiece of the serial device is going to be some ring buffers, which are going to isolate the simulated CPU from the code running in the background, which is actually going to grab these bytes and make them appear on our simulated console, or grab text from the simulated console and make it appear in the ring. I have some networking code that I worked on. I believe it dates from the 90s. I am not absolutely sure, and some of it has been tweaked since then. But the basic approach is the same. So we're going to end up with in the middle, we've got a ring buffer. Real simple. Boop, boop, boop. And it's got a produce hand and a consume hand. And the rules are real simple. You have a single producer and a single consumer. And the consumer can look at it and say, well, if the producer and consumer pointers are different, then I can consume the byte the consume pointer points at and increment the consume pointer. And I own that consume pointer. The producer can look at it and say, if I can increment the produce pointer without making them equal, okay, then I can produce a byte into the ring at where the produce pointer will point to, and I can increment the produce pointer to say this is now available. And the producer owns the produce pointers. Now, as long as your stores are ordered, so the producer guy needs to be able to produce into the ring and have it stored to the produce pointer appear to all consumers after it appears in the ring. As long as that is ordered, and as long as we don't read until we see them different, this is a lock-free structure. Yay! Well, semi-lock-free. If you fill up the ring, you're going to have a hard time. Also, if you empty the ring, you're not going to get a notification back that there's data in the ring. But we don't need that. We really don't need that. And here's why. From the 8080 side of this, this is a polling system where you say, are you ready to accept a character? And if you are, I will send you one. Do you have a character available? And if so, I want to grab one. So we're not doing interrupts with this. This is a polled serial port. And on the other side, we can say things like, I will only look for input from the remote end if there's space in the ring. And I will only look to see if I can output data if I have data in the ring to go out. So we end up with a ring each direction and data flows. The simulated device side of this can say, well, if the ring is full, I can set a timeout that says, call me back, let's reevaluate in a fixed amount of real time to say, well, wait a minute, maybe we've got data. Maybe the simulation has consumed data from the ring and we now have space to put something in. Or maybe the simulation has put data in the ring and we have something to take from it. So our ring can stay simple. So let's build this byte ring. Get into ink and source. B and C. I'm going to call it B ring for byte ring. So we're going to bring it pragma once. Now we are specifically going to use bytes for everything here. It's kind of a scummy thing. One of my dodges in embedded 8-bit systems was you'd set up one of these rings and you would align your buffer, your ring buffer, on a 256-byte boundary so that literally the low half of the address of the byte was the index. So we end up with something that looks like this. Type def struct sb ring. Keep wanting to type ring instead of b ring. Okay, so here's our beginning of defining the data type. And I am going to let the build loop know that it has a new file it needs to be looking at. I'm not sure it compiled that. There we go. Warning, struct has no members. Okay, so there's a couple of things going on here. I need a byte for the producer, a byte for the consumer, and I need a data of 256. So we could index into data by any unsigned 8-bit quantity. Now, in a larger system, if we were juggling a lot of rings, we would put all of the data buffers contiguously, so they're all properly aligned, and then we toss the prod and cons elsewhere. And this means that we can do some easy things. Now, in this case, the 8080 code isn't actually accessing this, but I want to write the code as if it was, because we may be deriving some 8080 stuff from this. Okay, we are re-indebted. So what do we need to do with our B ring? Well, we need extern void B ring init. I'm going to use R for the variable because I want to emphasize that it's a B ring, not a byte. Okay, so there's R. What we need to do there is, well, first of all, are our rings going to have names? I don't think so. So let's make sure we're starting in a well-defined state. So R prod is equal to 0, R cons equals 0, and I'm going to say memset R data 0, 256. So the weakness here is, what if a byte is actually able to access more than 256 bits, or 256 values? Well, goodness. We can toss that in one of our tests. So inside test, bring test.c. Okay, so what I wanted to do here was, in order to verify that, in fact, these couldn't access off the end of data, they could access, I want to make sure that byte can access all of data, can't access off the end, and so on. Actually, B ring, these guys don't actually get past a B ring. That was foolish. Okay, so if we ever mess up and for some reason the size of anything in this B ring is not exactly 1, we're going to have a bad time. So let's see, assert 0 equals byte of size of R arrow data. So if we take size of our data, we want it, and convert it to a byte, we want to get back a 0. If we take the size of -1 and convert it to a byte, we want to get back the same thing. Why am I doing all of this? Let's just do that, because in any reasonable projection of the future, if we were to come up with a situation where indexing into data by a byte failed, then something here would be failing. So as long as size of all these things is 1 and size of this is 256, for this to fail, the size of a byte on the native machine would have to be something other than 256. So let's actually put in this one last thing. 0 is equal to size of that. Okay. Going to do that also. So in theory, if we were compiling this for a machine with 6-bit bytes, all of this might still be correct, but this would fail because it would cast this and we get back 63. So we're good. I will revisit that and verify that it is more correct. The instant somebody brings me any evidence that we'll ever want to compile this code to run on any computer that has a byte that is not 8 bits. Okay, deal? Deal. So this means we are now safe. Let's actually put in something here that says pound define bring capacity 256. So I'm going to be making use of the fact that if you write expression modulo 256, I'm going to be assuming that the compiler is going to be swift enough to mask it properly. Also, I'm going to be using the fact that if I write expression and cast it to a byte, the compiler again is swift enough to do the proper masking if it's necessary. So there's our init. We start off with everybody at 0. Then we have extern int bring can read. Actually, bring empty. I'm going to put 2 full. So 2 status check things. Are we empty and are we full? We are empty if r prod is equal to r cons. So we are producing a ring that can carry up to 255, not 256. So let's set the capacity to that and adjust everything else. Okay, so this is cap +1 and cap. There. Bring full is going to be, if I were to increment prod, would it be equal to cons? And again, notice that if we increment prod by 1, cast it to a byte, we do this cast because incrementing prod by 1 may go off the end of the ring. 255 to 256, we want to wrap around to 0. So if prod is 255 and cons is 0, we want this to say full. There we go. So we're starting to write things here. Let's actually hook ourselves up. Inc. We need to hook ourselves up as a test. We're not hooking to the inside of i8080 anymore. This is a normal test thing. So source main.c. This calls into main post and main bist, which are in test main.c. It's been a while since I've looked at this code. And where we have i8080, I'm going to duplicate it and replace the word with bring. So we're adding the bring test down at the bottom. Bring is a fundamental data structure. We could push it way up in the list. In fact, bring is so trivial, we could do it first because it depends on absolutely nothing else. Let's do that. We're going to find bring, kill it off, step back to, say, RTC, and put us before it. Now at the top we have a power on self-test of tau. I'll run that first because tau is really special. But bring, then RTC, then step. Let's check that RTC. How fundamental is RTC? Yeah, I think bring is actually a simpler data structure than RTC, so we can test bring first. So if we let this compile, we come back with implicit declarations, okay? Because we need to pound include bring.h here. We still have implicit declarations. Because I didn't put them in here. Extern void bring post. Extern void bring bist. Oh, and do we want to benchmark bring? I don't think we want to benchmark bring. It is not a timing critical mechanism because one way or another it involves eventually moving data to or from a physical device, or, excuse me, a simulation of a physical device which is embodied via transfer over the network to a window on the screen or from the keyboard back. So we don't need to benchmark it. Actually, let's put the header file up here. Put the implementation over here. Now, I've stressed a couple times now that this is a trivial data structure, how simple it is. So we're spending a lot of time on it because it's going to be important. And that time is not going to be proportional to how easy the data structure is to envision or bring to the table. So bring empty and bring full. So after we do the assertions here, I'm going to say bring init of R, and I'm going to say assert. I am going to assert that it is in fact empty. And it is not in fact full. We are getting there. Now I'm going to push some bytes into the ring. Well, how do I do that? We first need to define the functions. Extern void, bring prod, bring, and a byte. So bring prod is going to start off with, it is an error to call bring prod if the ring is already full. So byte at is equal to rprod plus 1, assert at not equal to rcons, and then we say r data of at equals b. This is an assertion I am going to make. It is good to test that. Because it means that somebody didn't call there. So if you're going to call bring prod, you either have to say, if bring is full, don't do it, or you have to know that the ring is not full. And the same thing with cons. we're going to sample cons. And we're going to say our cons equals. And I do need to say byte. Well, we could do the same thing here. R prod. I go to R cons, and I can say return R arrow data. Oh, I need to be absolutely sure that we fetch the data byte before we increment it. This could be tricky. So we need to make absolutely sure to do assure compiler does not swap these, does not defer the read above after the write below. So one way of doing this is to start declaring things volatile. Volatile tells the compiler that somebody else may change these things behind our backs. Also means that we do not want to be referencing these things multiple times, because the compiler will no longer be able to optimize it. If I say rcons twice, it has to fetch it the second time now. So with that in mind, what I'm going to do is I'm going to start doing some things at the top of the function. So empty if they're equal. They're full if prod plus 1. Is there. For consume. So declaring these volatile means we don't have to put a lock around this structure. Yay! I love doing lock-free structures when we can. So there's, oh, the other thing is we would never be able to test that. Trying to induce a timing clash between two threads in a test system is extremely difficult. Especially in these multi-core systems where we may have separate cores on the CPU running the threads, and they may be running them at different speeds. So trying to jigger them back and forth so you get one, if you get one of them writing its index before it writes the data just a little bit in advance, and you get the other reading it, or you get something where, because of the way the memory architecture is, the write to the data happens to be completed before the index is changed. Write to the index happens to complete before you write the data. You can get the wrong person seeing the wrong data. So the volatile sols are hazards. And we're using plain assert here. So now I'm going to write 3 bytes and read them back and make sure that they're correct. Bring prod R1, 2, and 3, and we know that we are not empty. And then we are going to say assert EQ integer 1 bring okay, so bring cons and prod. Oh, cons was not set up yet. There we go. Test condition failed. Hey! Yeah, so I already have a bug. How about that? So everybody starts at 0. I do a prod. Yes. Producing to the wrong index. So we produce, and then we increment, and we consume, and then we increment. Now, we could go the other way. I could do pre-increment and pre-decrement. Actually, that sounds like it would be a way to do it. No, I still need to increment this. Yeah, +1. And this would be there. Pre-increment there, so cons equals cons. So prod and cons now don't point at the data. So prod will point at the most recently produced data, and cons points at the most recently consumed data. So we prod into index 1, and we consume from index 1. Well, that's interesting. Seems to me that if I did that so that it worked on the first one, it should work on them all. Okay, I give up. Going back to next. So okay, I'm going back to the original design because that's the way I think of rings, where you produce to where the produce pointer is and you consume from where the consume pointer is. So there. Notice when we increment, we always increment into another byte. I'm going to make this really explicit. Okay, so that passes now. You see a lot of explicit stuff like this with volatile and explicit reads when you're talking to registers. So from the point of view of the simulated device, we will be talking to the ring, and this is the B ring is an actual set of hardware registers we're poking at, and they can change behind our backs. So we're simulating a device here called a B ring. Think of this as a little chip we might install, a little piece of discrete TTL. So probably could have done the same thing by declaring volatile pointer to B ring, but it's much better to emphasize this because this means that we may have some things in B ring that are not volatile. So it's my habit to mark the registers themselves as volatile rather than saying that we have a layout and, oh, this pointer points to somebody who's got volatile behind all of that. Either way actually works. It's just that this way is easier. Also, if we're using B ring like this, how do you say this is an array of a volatile array? We would have to actually, it would get weird. I wonder if I can say volatile here. I don't even think that's valid C. That is not valid C. So there's B ring. I'm going to make this post. We're not even going to have a BIST for B ring because if B ring is so simple, it's going to be kind of like tau. So we go into test main test.c. We have a post. We do not have a BIST. Inc bring.h is over here. So BIST doesn't bring anything else to the table for us. We'll just do that during post. Oh, almost forgot I need to check capacity. So we're going to do this again. Empty and not full. We're no longer empty. We're no longer full. At the end of it, I am going to do one more And we are now full. Need to start at 1. Otherwise, we will actually bring it to capacity. There we go. And that should bring us back to empty. Okay, so we have verified that we can go exactly to full, and we can come all the way back to exactly to empty. If we tried to go any further than that, we would have bored out of the test, which is not what we want to do for testing. So we now have a B ring. Is there anything else I want to do before committing this? Yes, I want to put in some comments. B-ring init. How about to do write function comments? So for what I am doing now, I can look at this and understand what it is, empty, full, prod, cons, and so on. And this all makes sense to me. I believe I need to update .indent.pro. We probably have a whole bunch of type defs that we haven't put in here. This is actually still still indenting okay, even though I didn't put these. I thought I was going to have to do -T for every type def to get the indent profiler doing the right thing, but maybe I don't have to. So I'm going to commit that really quick. Stage all changes. Summary is add B-ring. This is a ring of byte indexed by byte values. So it has okay, inc bring.h, source bring.h, test bring test.c, and main test.c, bring.c. There we go. So there's the ring. Trivial data structure still takes us a while to build. It took 45 minutes. This is probably the simplest data structure, simplest absolutely non-trivial. The most trivial data structure would just be like a storage for a byte. Okay, so there's B-ring. I didn't show the get cracking on the screen here because it wasn't really important. Okay, so the next thing is we want to produce a character device. Going to call it cdev. I need to take a quick bio break. I'll be right back. Okay, we're back. And I'm ready to start on this character device. Interesting thing on character devices. My first introduction to doing actual device interfacing was writing device drivers, which ran inside a Unix operating system. It was Sun OS at the day. And you had two major kinds of devices. You had a character-oriented device, which would be things like a terminal or a printer, where you would send one byte at a time, or you would send a stream of bytes where the assumption inside was you would send them in order. So it was all character-oriented. Contrasting with this are the block devices, where typically your device would want to do DMA. A character device you might literally be doing, write this to the port, write that to the port. Block devices didn't operate on single characters. They operated on blocks of characters, blocks of data. So this might be the size of say a sector on a disk. And the assumption there is normally this would be DMA, where you'd say, hey, disk controller, please read track 32, sector 15, and place it at this address in memory. And later on, it would come back and would tell you, hey, I'm done. I have read that data, and it is in memory now. We'll do block devices probably next session if we get the character devices done this time. So what do I need for a character device? I think I'm going to give it a name so I can print stuff out. So CSTR name. I'm going to need 2 B rings. Maybe some character devices will only use 1, but that's okay. Going to have an RX ring and a TX ring. So RX ring will be data from the device to the simulated system, so into the simulation. TX is going out. This is from the point of view of the program running on the simulated processor. Okay, so we have a name, we have a way to receive data, we have a way to send data. So now we need extern void cdev init. Let's put in a post. and a BIST. Again, this is a device. They are big and slow and clunky. They only do occasional bits of data. There will be no BIST. So things we want to know about the CDEV. Well, it's going to have some of the same kinds of entry points as the B-ring. Let's put that in here just for that. But it's slightly different. So extern int can rx and can tx. Those are the important ones. Then extern void, extern byte rx. Now the difference is that these are being spread between two rings, so we're always receiving from the Rx ring and always transmitting on the Tx ring. CSTR, where did I define CSTR? Support? I think it was in support. That also means I need to have a CSTR. Oops. There we go. So initialize it, it gets a name. Why don't I give names to my B-rings while I'm thinking about it? Work the name in here, CSTR name. Not using the name for anything yet, but this means that if we want to print out something about a B-ring, we can include its name in what we're printing. Oops. Integers in lowercase. There we go. Oh, I must have upcased everything by accident in here. Can I undo past? There we go. Problem with an editor that allows you to do things like uppercase the entire buffer is sometimes you accidentally do it. Okay, so we now have a name in our B-ring. cdev.h. We have a name. We have an Rx ring and a Tx ring. We say, can we receive, can we transmit, transmit. We have dev and we have bist. I think that's all we need. We go over to cdev.c. And we need to define these guys here. Okay, now I removed a file. Let's make sure that this loop is doing the right thing. Make clean loop. There we go. And over here in cdev test, we need to define these guys. So cdev init d arrow name is equal to name, assert d name, because this is an actual device, I'm going to be a little more paranoid. And then we say b ring init of d arrow rx as format. And tx. Okay, can rx is return make sure I get the names right. We can receive if not b ring empty of d arrow rx. We can transmit if not b ring full of tx. Notice I'm not asking, is the device full or empty? That's bogus. I'm asking, can I transmit? Because a terminal is never full or empty. Now receive says return b ring consume d arrow rx. There we have it. There's our implementation of this side of the thing. But that only talks to the rings. We need a thread running in the background that connects up these things with somebody else. So I need to have some additional entry point, cdev connect. What do I want to connect it to? I want to connect it to an internet. I want to connect it to an IP port. So cdev itself is going to be a TCP client. There's a TCP server that I already have out there and running, which is actually a terminal multiplexer. Now let's actually turn on my view of the TTY. There we go. I have a simulated teletype sitting on localhost port 2501. And if I connect to it with TCP, it will gladly connect to me. And if I send it a byte of data, it will print it. And if I reach over here in this terminal and I start typing things, it will send it to me. The teletype is set up so that it doesn't print what you type. So you type something, the host system has to echo it back to you for it to appear on the screen. I don't remember whether, I literally don't remember whether teletypes worked that way or not. Literally. The other one I have is a video display terminal. Now this is actually set to a specific size. It's 16 lines by 64 columns, which is the size of many microcomputer video displays of the time. It takes up 1 kilobyte of memory, and the low 5 bits will address the column, and the next 4 bits will address the row. Oh, excuse me, low 6 bits are the column. This makes a lot of computations fairly easy. It also means that you can build a video display, build your video display hardware, so that you just have a 6-bit counter for your character, and it fetches the byte, and then you take that byte and you index into a ROM that has the font, and the bits come out of the ROM, and you do a shift of those out at the right rate, and it paints the nice rasters on the CRT. Anyway, so that's why 64 by 16. 80 column takes more work, which is why 80 column cards were kind of the deluxe thing. I could very easily do a similar thing here, which is 80 column. Wow. Anyway, so I am actually on the on the fence as to whether I want to do this. This is actually simulating a external video terminal over a serial link, and I think what I'm going to do is I will focus on having a printing terminal here, and if we want to do a video display, I will actually have a simulation that has a kilobyte of memory in the host that it displays, so that then we would write the software inside the host to simulate doing the math and writing the byte into memory, and then we would have that display out there. The trick of that is that I would want to actually have, instead of a terminal like literally that's running extern. Okay, what I would do instead is I would have to have something mapping pixels, or I would have to say it's strictly a character display and then use curses to put the right character in the right place. We'll see. Anyway, we'll focus on the TTY stuff. So currently, if I were to open up a connection to port 2501, I would be able to move data. So over here inside my software, I need to have a port number. I'm going to allow any, actually, let's allow any port number. No, let's not allow privileged ports. And I think I'm going to limit us to be less than that and greater than 1, 2, 3. I think above 48K are multicast. Then there's some dynamic ports. Let me double check this. Might be good to actually limit ourselves to ports we can use. So bring up a browser, TCP port numbers. I used to know this right off the top of my head, like not even without thinking about it. Okay, so Science Direct isn't really what I wanted here. List of TCP and UDP port numbers should also include definitions of port number ranges. Well-known ports. This is giving the individual well-known port numbers. The table from the IANA. I'm not going to map my browser up. I'll just use it. So the first, up through port 1023, those are all considered to be privileged. Many operating systems won't let you bind to that port number unless you have privileges.
Okay, she's
Then we've got a bunch of registered ports, or people have said, my application or my service is going to use this port number, and if you register me, that means everybody knows where to find me. There are bunches of these that are unofficial. There's bunches of them that are reserved, and starting at 48K, we have dynamic or private ports that cannot be registered by IANA. So private or customized services, yada, yada. Dynamic port numbers come from that range. So what I will do is I will say, I am going to run my service at some port all the way up through 64K. So 1024 through the end. And in fact, we are connecting to it. We're not trying to bind to it. So I could just say there. I don't believe port 0 is viable. I think port 0 means pick me a port in a lot of cases. Yeah. Port 0, the quote here from IANA is, in programming APIs, not in communication between hosts, requests a system allocated dynamic port. So if you use port 0, you're not going to get port 0, you're going to get something else. So we won't allow port 0. I don't think you can bind to port 0. Anyway, so we will allow ourselves to connect to any of those. Next thing I need is to get my little reference information on TCP, because I now need to put in a TCP client. You know what I didn't do here is I didn't do an invariant. It's been a while since I've done a real thing. So now we're going to say extern void cdev invar. We do not, there was the other entry point which was linked. I don't think linked is going to be used for much, but now we need to say cdev underscore con int port, like that. If we call it TCP port, it'll be more clear what it's for. Oh, and invar we need to set up. Now, the neat thing about the way that I chose the data type for cdev is that every possible arrangement of bits inside the B ring is valid. But we can also say B ring invar of D arrow RX and TX. You'll notice that I forgot to do the invar for here as well. Invar and linked I didn't do. Let's set them up. And actually, I think the thing I finally settled on was often the invar may or may not be something you'd want to call before linked, but sometimes you do, so we're leaving it like that. Now, I could force the invariant check before each and every one of these things, because these are not timing critical. Furthermore, I could also set the invariant, check the invariant there. Not a bad idea. That way, if I break my own code to the point where the invariants are not being met, we've got the right stuff. We're not changing state. Can I declare these const? Is that even a thing? Haha, need to declare it here. Linked wouldn't want to be a const. Yes, I can declare those const to assure that those particular function calls do not modify the content, do not modify the state of B ring. We're going to do something similar here. So cdev con, I think this is going to be const as well. Because when you start somebody doing this, they're going to be manipulating the ring. Well, that does mean that the thread that's doing the work needs to have a non-const pointer to dev, a non-const reference to it. That also means that we may add more state to the cdev so that it might know about its TCP connection. Or we might just keep it completely separate so that cdev itself does not know what mechanism is mucking around with the contents of Rx and TX behind the scenes. But we're going to do the implementation here. And now I can get in here to my reference code. Let's see. This is actually very much elsewhere in my projects directory. Very, very old code. Let's get the one from C99, TCP client. Because setting up a TCP client is, it's not trivial. It's not as hard as setting up a server, but it is there. So first thing is we need to create a socket. Okay, now that's not going to compile. Because we haven't got the header for that yet. Socket is socket.h, I think. Yeah, socket.h. No, it's not socket.h. Syssocket. I was looking right at it, and my eyes just kind of ignored the sys in front of it. Okay, so con, that gets us a connection. If con is less than 0, then we want to do stuff. I'm going to set up another macro real quick in support.h. There's something pound define fin. Fail if negative. So we're going to declare a variable called var, and we're going to call a function called func, and yeah, just triple dot. This is using the same stuff we used up here. And we're going to declare int var equals func of VA args. Hey. Hey, Tempo Dude. Stay safe. Okay, so get back to this macro thing here. So we call the function now if var is greater than or equal to 0. I'm going to set this up so that we can little bit of magic. I want to be able to put a semicolon after this guy, but I don't want anything else, and I want it to be able to fit inside an if with no braces followed by an else. And that's the dodge we use right there. And in this case, what I want to do is I want to report the error. Now we don't need to have the source code and file name and the line number and all of that, but we do need to print what was going on. Okay, error %d from there. I wonder if I can get the parameter list out there too. Okay. So there's a fin macro. I do want to test it at some point, but we'll use it right here. Fin, con, socket, and the parameter list. Now, if I've done this correct, I could do something like if something fin else print. So syntactically, that should be correct. So my idea was that if you write this, it should work. And what's happened is expression before int. Because you can only declare a variable if you are inside. Right, so this, right. Okay, I can't do it for fin because fin has to have the int var in there. Never mind. So we don't need to jump through those hoops for fin. Yay! We just say if. I am going to jump through one hoop. What this does is it makes sure that if somebody wrote fin, no else would even be, even that isn't necessary because that would be a syntax error if somebody wrote something that required that dodge. Okay, so now we have our first use of arrow in here. And our first use of abort in here. There we go. So now I can just write fin variable, the function we're calling into the system and its parameters. This is because a lot of service calls in Unix return an integer where negative is a failure and 0 or positive is a success. In fact, of all of the system calls, the only one that I thought was important or interesting that didn't follow that was the mmap call, which returns 0 for failure because any non-zero value could be a valid pointer. Rolling the eyes. Oh, well, the things you have to face when the potential return value of a function is almost anything. But you could say negative because you are getting back a value that needs to be cast into a pointer. So there's our creation of the socket. Now we need to connect to the server. Now we need an IN. We need a sock adder IN. This is an internet style socket address. Sock adder is a big structure that could be any one of a number of different kinds of addresses. We'll just call this SA. Make sure to get it all zeroed. It's an INET address space. The address family is INET. It's a.synadder.sadder is going to be a 32-bit value, which has to be converted properly. We're just going to use 127.0.0.1. This is the IPv4 loopback address, which is where our server will always be waiting. I'm not going to use localhost or anything else. I'm just going to wire in the loopback address. The port number has to be converted from host order to network order. Okay, your sock adders are actually a bunch of bytes that are properly organized, and the byte order for the internet is big endian. The fact that so many CPUs are little endian and things went that direction never ceases to amaze me, because when you write words or numbers and you want to sort them, the first thing you look at on the far left is the most significant thing for the sort or the numerical computation. Which means that if you've got little endian data stored in memory, you need to scan all the way out to the end of it to figure out what's going on. Anyway, synport. Some of us are a little more big endian big Indian friendly, little Indian hostile than others. So once we've set up the SA, we define, and the only thing we need the connected value for, we're going to call connect with our thing we did up here, which is con. This is actually the socket number that we will be getting and using. Now, I like the idea of using SA sub 1 here. It comes out to the same code. So we're going to declare a variable to get the return value from the connect call. But we're going to continue using con, so we don't actually use connected for anything but error checking. Array type has incomplete element type, struct sockadder in. Well, that's because we have to do yet another #include, because there are so many different kinds of socket addresses. It's set up so that you can create new address families. Well, we could create new address families. And the address family we want is the iNet family from the ARPA network. If you don't know what ARPA is, what are you doing on this channel? Never mind. ARPANET is the Advanced Research Projects Authority, Association, whatever. It was the original project for doing internet stuff, internetworking. So connecting, you had a local area network at this facility and a local area network at that facility. So internetworking is where you connect them together and allow data transfer between them. That was done by ARPA, which was a U.S. military thing that later got turned into a number of things. There was a commercial push to make it general. The government kind of put it out there and got it going in the mainstream. And I think it was NSFNet for National Science Foundation. Anyway, big research thing. And about 1987 or 88 or so, we started going downhill. And eventually, we got the net of 1 million lies, which we have now. Well, wouldn't trade it. Wouldn't trade it for the world. We're so dependent upon it now. But yeah, we've come a long way, but we still have that legacy here. This is still ARPA in this header file. Because once you've done something, you can never undo it. So let's see, we get our connection. So if we manage to connect here, if we didn't manage to connect, we are going to crash. I mean, we are done. If we are setting up a simulation that requires a line printer out there and we can't find it, we're done. So there's connected. And now we need to pass this off to a thread, which is going to start moving data back and forth. I'm going to call it CDEV SRV. So this is going to be the structure that I use to communicate information to the thread that it's going to run with. Actually, no, I'm going to put the information that my thread will need right there inside cdev.h. Yeah, okay, we're gonna do this. So we need to have a int con socket. I'm going to need a pthread. Hold on. I have some other code that uses pthreads. Is pthread T? Do I even need pthread T? Yes, I do. So the results of the start call is actually pthread create.
No, that was.
It returns -1 for error, so we use our fin macro.
I think. Yeah. Oh, yeah. It was. I hope she's already dropped.
Okay,
But she's even got the
no.
on yet now.
There's a parameter inside the pthreads right there that I just don't use. Then we have a pthread main
Right now, that was my last
FN,
ring tag.
which is going to be cdev server called service,
Another tune coming up. Don't worry.
and void star is the dev.
I have a 53 druid.
Now the functions that pthread wants have to return a void star. They take a void star as the parameter, like that. So I just declare that to be the function type. I'm not going to wrap that in parentheses and put another star on it. I don't need to. I can do that in the cast down here. Void star pthread cdev service. And what I'm going to take is a cdev d. Okay, and that's static. So I can put it down there. So my function is not precisely the same as the kind of function that it wants. How dangerous is that? It's actually not that dangerous, but it's still let's not do it. Let's actually declare it to be of the appropriate type. Oh, come on. And I can put this up at the top where all good C programmers put their declarations. Port number, this is actually TCP_port. Okay, pthread create is not defined yet because I need to #include pthread.h. Unused variable D. Actually, let's say stub hello my cdev is %s. Boom. So let's go back to cdev test.c. So cdev post probably won't connect to anybody else. cdev bist I will be connecting out. cdev underscore con. Let's connect it to the TTY 2501. We need some way to shut down a cdev properly that also shuts down its thread. So I need a cdev fini, or cdev close. Did I ever build a linked? I did not. I'm not going to use one. Let's put close up with init. So init is going to need to also set d arrow con equals -1, d arrow thread. I believe, yeah. Don't even know if that's legal. Okay, so apparently pthread t happens to be integer-like. Let's leave it at that. I'll use con being -1 as my flag for whether thread is going to be viable to look at or not. So if it is indeed true, we'll need to do something to cause cdev service to do assure service thread terminates when needed. Actually, while d arrow con greater than or equal to 0. There we go. So if con ever gets set to -1, we will eventually bop out. Okay. So now the process of closing this will be close d arrow con equal -1, join d arrow thread, I think. Hard to find in the manual when you use the wrong name. Let's see. pthread join. I'm going to mark this as volatile, so any indirections we do through there will always be done. switch. Select. Hell, let's go ahead and put the select in as long as we're thinking about it. So one way to do this is to have a thread for each direction. Each one blocks on its input, and that sort of works. But the other way to do it is to have a single thread which uses select to figure out what's going on. And we're going to do that one. Notice I like that array of one. That's mainly because I started out in Fortran where identifier really represented the address of it. Okay, FD0 of read FDs. Okay, so we don't want to just blindly wait for data to be available if we can't put it anywhere, right? So we say if B ring, let's bring so if B ring not B ring empty of the RX ring. So if the RX ring is not empty, then we want to notice data coming in on the connection. Just like that. If the T ring is not full, no, never mind. So if there is space on the receive ring, we want to notice the data ready to come in. And if there's data available on the outgoing ring, then we want to notice the ability to write. TV. Actually, let's set this to 1 second for now. So if we don't have any reason to wake up, for instance, if our transmit ring is empty and our receive ring is full, then we'll just sit for a full second. Later on, we'll change that to something smaller so we can check more often for the ring doing something. We can't get woken up on the ring changing, unfortunately. So these guys, I could declare these outside the loop. I'm going to. It doesn't really matter, but style at the time for me and the people I worked with was that if you had something significant size, you didn't declare it inside a scope because there were some compilers that would actually yank around the stack pointer when you did that. In fact, even this was sometimes considered to be a no-no. But it's so important to me now that I just do it. So we set up the NFDs. It's okay to put NFDs in to be too high. It'll go up to that many. So we could literally call select with those empty and it would still work. And the parameters to select are NFDs, read FDs, write FDs, exception FDs, we're not checking for that, and TV. Okay, if cell is, so now we say if cell is greater than 0 and FD is set con read FDs. If that's true, then we know that we have data available on the connection coming in, and we also know from up here that we have space on the ring, because that ring, if it had space then, it'll have space now. So I'm going to need a character buff. Actually, this is a single byte. Hello, Lucy. Hold on. I've got somebody who wants to do a code review. So, Lucy, we are in the middle of writing some code. So let's take a look at it real quick. In the service function, which is running in our second thread, you can see it there. Basically, we check and make sure we still have a connection. And then we very quickly say, construct NFDs and set our FD set up for that connection number. So we will notice read data if we have a place to put it in the RX buffer. And if there's any data in the TX buffer, we'll say, notice if I can write. We call this select will return the number of bits that we're on. So it goes through and says if a bit is set in read FDs and it's ready, leave it on. If it's not ready, we turn it off. Same thing with write. So now if we had any bits set in the result, if cell is 0, we're done. We go back and loop again because it waited the timeout, right? Right. If cell is greater than 0, then, and the bit for the connection is set in the read FDs, then we go do a read, and then we're going to put it on the ring, and we're going to decrement SEL. And then we're going to do the same thing for write, except we're going to take data off of the ring, put it in CB, and then we're done. The write, put in CB and do the write. Got it? Okay, she looks like she really just wants to go crash out somewhere. If she consistently sat in her box while I was coding, I would set up a kitty cam right there. So we do the read. Now, if RS is less than 1, I'm going to break out of this loop. So if we ever do a read from our connection and we get back a -1, we're done. If we didn't, then we can say ring prod of D arrow RX okay. We decrement cell, so now cell will be 0 if that was the only bit. Something similar, write FDs. I'm going to need a byte. Oh, wait a minute, I can actually say CB sub 0 is equal to ring cons of this guy. So we're going to consume a byte from the ring, put in CB 0, and we're going to say write. Same thing. So if we try to write to the connection and we get back a 0, we're done. And what I also want to do here is there. So at least initially, while we're debugging with it, I will print out everything I read and write. No, I want to just do that. So this isn't going to actually inform the rest of the simulation that we have lost connection. That may or may not be a good idea. If I set con to -1 here and return, the other guy will not have joined me, but it won't do that. Well, it's going to terminate anyway, so let's just do that. Implicit declaration of function close. Standard lib.h, I think. Oops. Unistandard. pthread join, too many arguments. Pthread join, I think the second parameter is where to write the return value. Yeah. Okay, TV is a struct time val. I'm going to make it an array of 1 so I can use my arrows. Fix up typos. B-ring prod. I'm so used to this data structure being called a ring. Why does this keep... Emacs keeps putting pthread in a different font. Okay. still showing my I'm still showing my TTY on the screen. Good. So we're not calling cdev test yet. Let's fix that. This is in test main test.c. So cdev will have a post and a bist, and it's kind of a big thing because it starts a fork, it starts a thread out there. Okay, so we got to top and we got to end, and nothing else printed.
Hello? Hello? Hello?
Okay, so here's our trace. Socket is getting a garbage value because socket is a function name. Con3 connected to 0. And, oh, I didn't notice, but yes, on the terminal over there, we in fact accepted a connection and terminated it. And yay. Okay. So the next step is to have the test sit and do something. So what do I want the test to do? There's cdev test. There's cdev.c. Actually, let's base it on the there. What I'm going to do is I'm going to say while not can rx of d. Actually, let's stop using sleep here. Let's use usleep. I just want to not soak up all the CPU. Okay, so we're going to sit there and do nothing until we can receive from the device. Then we're going to say b is equal to rx of d. If b is equal to some value, I'm going to return. How about an escape character? And we got that, and then we're going to say while not can tx of d So basically, our test is just going to be to receive bytes from the device and echo them back until we have an escape. And we will not echo the escape, we will just close at that point. So the live coding, the live loop actually got there first. And it's doing nothing. Ready to connect. And I am typing on it and nothing happens. Probably because it's being routed to that stuff. But the escape isn't getting through either. So we're going to terminate the live loop, and over here I'm going to go to my quicker thing, which is basically make, and then bin/live coding bist. Connection refused. Okay. Try it again. So we accepted the connection. Over there on the left, let me move that to the middle panel. So we saw connection 3 connected to 0, service initiated, service terminated. And then we printed that. Somebody set con to -1. Next question is why? So we initiated -1. There's where we close. Oh, right. Okay, connection refused. This can happen if you try to reconnect too quickly. First of all, my thingy here, if I just say terminated like that, that I'm printing when I lose the session. I then wait 3 seconds and say ready to connect. And it's that point where I'm actually listening again. So, okay, we got it. 1, 2, 3, 4, 5, and it's doing byte by byte, and then I hit return and foo bar, and that's good, and I hit escape and we're done. So this now says bad file descriptor. So we've got an error from select. I wonder if it does that. Well, once I hit the escape, oh, okay, so if I do, when I do the close, yep, there's where I close the connection there. And we are in a select while we are connected. So what I need to do We don't actually get to close until we're there. So byte, let's see, int con equal d arrow con. We're going to keep the connection open, but by setting this to -1, we are stealing the connection back. But the connection's still open, so that select won't be terminated. Calling select. Come over here, A, B, C, D, E, 1, 2, 3, 4, return, and we hit escape, and here we go. So we see RX1PH service terminated, joined, and done. So that shuts us down nice and gracefully. But what I'm not seeing over on the printing terminal is I'm not seeing the return data. I am calling TX here. B-ring prod TX, there we go. So I'm surprised that that didn't loop us infinitely there, because we then produced our byte back onto the RX ring. Natty naughty. Now we go back over here. 2, 3, 4. Oh, assertion prod not equal to cons failed. Oh boy. So somebody's calling bring cons when there's actually not space on the cons. Let's put asserts into both these places. So assert, not be ring, empty. Wait a minute. Is that correct? I should be using my cans. So this says oh, nope. This is the service loop. Ah, there it is. TX. So this is the RX. This is all RX. This is all RX. Okay, this is all TX. I can get rid of these assertions because they're being done inside the bring stuff. Okay. 2, 3, 4. Oh, goodness, check this out. It is echoing, slowly, but it's echoing. I need to change those select timeouts now. Now if we hit escape, we are done. Session terminated, ready to connect. So the timeout is 1,000 microseconds here. And these are already set to 1,000 microseconds. That would be 1,000 hertz, so we're not doing it. We'll leave the rest for now. Accepted connection, so 1, 2, 3, 4, ABCD, foo, bar, baz. And escape ends the test. Okay, so this is a manual service test. It's not what I want to do to actually test the thing. In order to test this part of CDEV, I would need to incorporate a TCP server for that port locally. Don't want to do that. So what I will do is I will bypass it. So we're not going to connect. Meaningfully, what is it I am testing here if I'm testing CDEV? I would be poking at the CDEV API. CAN RX, RX, CAN TX, and TX. These basically just test a B ring now because I would be exercising these, and on the other side I would be checking the state of the ring. So this would be just tests of the RX and TX. So CDEV doesn't actually have meaningful post and BIST at all. I'll call this test. What we're going to do instead, so I'm going to add a thing here. It says if not strcmp of CDEV. So CDEV test is going to take args. It's going to look just like the main stuff here. So this is going to be test main, test.c. Ba-bum. Okay, so now I can say make and test CDEV like that. Bin live coding CDEV over on the left. Connected, CDEV service initiated, and there's our instructions. So now we go over, I type, this is a test. We have all of our crap being printed. Now you hit escape, and session is done. And there we go. So let's get rid of some of the stuff we're printing here. Since we know that it has worked at least once, let's leave stubs here in these error conditions. So in those error conditions, I will do a stub print so we see what's happened. If we get a normal termination, I will print this. And now we're running our test again. And there we go. So this still is printing stuff because there was an error on the compilation, which it did not print here. Right, because if you just do a make, it's just tucking it away in the file, not printing it. So let's see, return CDEV test of whatever. Value not ignored because CDEV test needs to return an int. So I could do something like when I say run the CDEV test, I could give it a port number. For right now, we'll just stick with the TTY port. Okay, there we go. We test again. Session terminated. All done, test complete. And we had some prints, which I can get rid of. Okay, so CDEV is now working. But it's not yet hooked up to the system. So we have functionality. We're able to call the functions, but it's not yet a simulation module. Because we can't yet connect it to an I/O port. So that's the next thing. So CDEV isn't just this arbitrary abstract thing with functions. It actually needs to be able to connect up to a system. So what I want to do is now have we need a read signal and a write signal. Actually, what I need, registers needed. I/O device that has these ports. I'm thinking, do I want to have a control port that I can write to for CDEV? And in that case, what do I want it to do? If this is a real serial device, there are several things you do with a control port. You set your rates, set your start bits, stop bits, even odd parity, 7 or 8 bits of data, all of that stuff that we're not worried about here. We could set a data rate, which we would then use to throttle our input and outputs if we wanted. Don't think we need to do that right now. We might want to send a break signal. Okay, how do you send a break to the printing terminal? Well, we would, I don't know, I guess we would kill the connection. Anyway, let's specify I/O divorce that has 2 input as the following ports. RD sub 1 sub 0 is read the status port. So low bit is set if there is data available. High bit is set if we can transmit data. Okay. RD sub 1, read the data port. Returns the next byte of data. Let's swap those. So the first one of both is going to be the data port. I suppose I could go out and look at existing UARTs and model it after that, but all of them are going to have a whole bunch of extra stuff we don't want. So we're not going to do that. See, what would be a valid thing to do? Well, once I've put something on a TXQ, I don't want to flush it. I don't want to clear it without clearing out my thread, because my thread may have already said, I assume I have data to transmit. I don't want it crashing on me. Data is a command byte. 00 will be if I come up with something I want to do with a command byte, I will start putting them in. I'm thinking the possibilities are to have a way of shutting down the connection or a way of turning on a connection, which would mean I want to save off the port. So let's do that. So while we are connecting here, so in theory, once I have done a connection, the system itself could use port number to reestablish the connection, which means status would then need to have information about whether we are connected or not. Let's make this true if the device is connected. There we go. So in theory, I could say 0x00 might be disconnect external device. 01 is connect, reconnect. So disconnect and reconnect. I've got to mark those as unimp because I'm not going to implement them immediately, but we will reserve those command codes. So to implement that, I need to have some edges, p-edge, rd, and wr. Okay. Which means we now do in fact need a cdev linked. Now if invar is only called after we're linked, then invar will be checking some things on those edges. Put linked after invar so I can call, and when we're done, and we're going to say here, edge invar d arrow rd sub 0 and 1. Oh, wait a minute. These aren't inbound things that somebody else gives us. These are edges we own. Ah, right. Okay, edge. Make sure I've got this right. Edge init in uppercase does take E and V. Edge in lowercase takes the name as well. Read data, read control. Write data, write control. Now these guys, I want these to be matched up with the read and write from the decoder. Let's remind ourselves of what that looks like. So these are supposed to be active low signals. Like that. So we're going to initialize them to being high, like that. Now I've set up linked. I don't have any work to do in there yet, but we will have it because I may need to link it up to things like weight signals or whatever. Oh, data, right. So there we go. So data is not going to be valid until linked. So we can go in here and say p d arrow data is null. And on invar, I can do that. And we need to also assert arrow data. Edge invar discards const qualifier from pointer target type RD sub 0. Right. So edge invar needs to take a const. const is catching. Port undeclared, so TCP port, there we go. Okay, subs. Those are const. Which means subs invar also needs to do that. So I'm confused. How is that discarding the const qualifier when I'm tossing it into const p subs? Oh, right. It's a const pointer where what I want to do is a pointer to const. So does that work? Okay, enough fucking around with const. We're not doing it. We're not going to use const for our invars because just getting it all out, this has always been a painful thing in C. Having const in the right place at the right time and not in the wrong place at the wrong time. I suppose I could use const in some place. The problem is that you have const pointers and then you have pointers to things that are const. And they're different things. And getting the syntax right to get it all through the compiler is non-trivial when you haven't done it in a decade. So let's see, where was I? It's here in cdev.c. These signals were active low, and there's data. And I said invar was going to assert the data is not null. cdev test is not going to work now. Because now if I say cdev underscore linked, we may have a BIST available to us. I may want to write a test that does stub the back end. Yeah, we now have a viable BIST. So void cdev BIST. We will need to init and linked. We will not do a con. Okay. Oh, wait, a val works through CPU, doesn't it? And it's only for CPU tests. Right. So we're getting to see dev bist. Okay. So we're going to assert that our thingies are correct. There's what I need to implement now. So what I'm going to do is on the descending edge of those, I will look at the value in data and take the appropriate action. Or put that value in data, take appropriate end. So, but we're not going to do that until linked. Here's our statics. Let's put these at the very bottom. Well, no, they should not go at the very bottom. Let's see here. No, I could put it right where the comment is. Makes sense. Makes enough sense. What did I miss here? H. It is on edge on fall. Okay, so if we wiggle the edges, we should get into the functions. There we go. So read data. We're going to say if can, oops, how about okay, beef that up a little bit with some stub. So I made a mistake here. I didn't put the CDEV in front of these guys, which makes it very hard to namespace things properly. Okay, read control. Okay. So there's the raw reads and writes. Let's check this out. CDEV-WR. CDEV-TX. Okay, go back into our BIST. This is turning into an extra long stream tonight. But I feel like I'm getting a lot of good stuff done here. So, first of all, what I want to do is do reads and writes on each one. Let's just start from the top. RDD, so let's read the data. Now this should come back with an FF because we are empty. So let's start off with assert that we're empty. B ring empty D arrow RX. Okay, I'm going to assert that several times there to assure that the state doesn't change. Interesting. So edge low RDD, hold on. And we're getting into busy. Okay, so the question is, did I get these initialized? So cdev init did call edge init. And then linked edge on fall is calling these guys. And this is sending data to the data thing. So we're calling, oh, got it. The invariant says we're calling the edge invariant when we are not busy. However, that means that if we end up in one of these functions calling back into cdev and cdev calls its invariant, it's not going to pass its invariant because its edges, one of its edges, is busy. Which means I can't use cdev rx here. But that's the primary place to use it, which means what I want to do with the invariants is the invariant of, oh boy, Does an edge pass its invariant if it's busy? No, it doesn't. Which means we can't pass our invariant if we're saying our edges must pass their invariant. Okay. And tau isn't advancing. Okay. So if we're going to be manually bit banging these things, we do need to manually advance tau. Might help if I did a data edit, huh? Is there a macro? Yes, there is a macro. But I won't use it. No, I will. I'm not using it for the other one. There we go. So I had a random chance of that particular error happening based on not initializing data. So we're going to get a informational that the data was empty. So we confirm that happens. Let's do this again with data valid. Oh, right. We need to put it in the other one. So this is actually B-ring prod. So we magically make a 5-5 appear in the RX ring. It's not empty. We're going to get the 5-5 back in our data, and it will be empty. And we're seeing that. So the other thing I want to do Let's look at the control register now. So the value we should see here, we're going to be, I believe, 0, 0. TX ring, so we're actually 0, 4. And this is going to be 0, 6 because we now have data we can receive. And that's correct. This has been observed. And once we have consumed that, then we're back to 4. That's correct. Okay, now we want to transmit some data. In fact, what I want to do is transmit until the transmit queue is empty, is full. I equals 1, I less than the capacity. So before each one, we're going to check and make sure that we have TX is ready to go. We are going to data to data. I'm just going to send the I value out on the data. Then we are going to TX. So I don't actually have a way of pulling out the number of items in the B ring here. At the top of each loop, we should say full is 0. Before the loop, well, we are testing B ring empty here. So what we're going to do is we're going to look at the values in the ring when we're done. So RDD, this is going to be WRD. So there we have it. We're writing the data. I'm going to write one more. This time the 4-bit will be turned off. We're going to write this again. Okay, that tests all of the paths that I've marked as observed. Now, I think this last one is going to bail on me. Yes, so we are now empty. So this means we got precisely the right amount of data out of the TX ring. So the only thing we haven't tested here is the connection bit here. Do I want to hook it up there? This test could be done using the same mechanisms we used above. Yes, 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 yes. So we did the init, we did the linked. We're going to add doing a connection. And what is the dance here? We're checking the RX bit. So what we want to do is edge, low, RD, C, C is equal to data. This is a much better test because it's using the actual mechanism that we'll be using inside the simulation, even if it is going to be a lot more lines. So same thing again, but we're checking TX ready now. And now we are going to do a data to data B. There we go. And now we could repeat our earlier little live coding CDEV test. Please type your keys. And it's working just fine. And that is using all of this stuff, which is behind the TTY. I hope that wasn't too unclear. Let me hide my terminal. So there's what our new test looks like. This is the new manual test. We're now actually exercising the edges. So send the control low, grab the control signal, set it high, check the bit, and so on. We also want to say assert C ampered CDEV status. This was con. So if I do this again and I kill the printing terminal, literally I'm going to just terminate the window in the middle of the test. This should disconnect. Yep. So we get this, CDEV ended, read returned 0. So that is properly bailing out, and we get a failure here in the test. And now I need to restart that guy. This is dev-all.sh. Okay, we're getting bind errors that the address is already in use because a client is still connected to it somewhere. Fuser 2501. Whoops. What was the syntax on Fuser for a TCP port? Fuser just uses that. Okay, I thought it was Fuser that did this. It's apparently something a little bit different. Let's see. Linux, who has a TCP port open? Somebody's listening on that port. Oh, they are now, because we finally got it open. Okay,
Beaver
so
has the fishing pole.
if you abnormally terminate a server, even if you set the reconnect flag, it still will hold that port and reserve it so nobody else can reopen it within a certain amount of time. This assures that gives a good chance that you won't think you're connected to one server and suddenly you're connected to a completely different thing. It's a security thing. And we are back up and running. And terminate, and terminate. There we go. So the BIST is working. It's checking that we can run the stuff in and out of the rings. And the manual test is working. We can check that we can move it to and from there. And that covers the entire data path. We still have a whole bunch of problems in comments. So to do, add a lot of comments. There's CDEV. Let's take a look at bring to do, right, comments. Okay. I think we are ready to commit this and push it. Do I have a Kraken? Yes, I have a Kraken. Let's turn off the TTY and my cam, turn on the Kraken. And I am going to amend the prior change, so this is add bring and CDEV. So the TCP TTY server is as interesting for the project as the internals of Xterm. And the internals of Xterm are not interesting.
I'm running through right
There we go. It's going to have to be a force push because I am amending. And now we have a device that we can instantiate, and a simulation could instantiate multiples if they wanted, so they could set up one talking to a teletype,
The
one
other
talking to a
two,
video terminal, and one talking to a line
not a
printer,
huge priority for them.
and anything else where we're displaying things for people to read and accepting keyboard input. Something similar in terms of the front end of CDEV will be done to do paper tape punch, but instead of going to rings, it'll be dealing with disk files. And then something slightly different for block devices, where we will be moving blocks of data to and from mass storage. I think this is going to be enough for this session. It's 3.5 hours. That's a half day's work. Wow, this project has turned into a part-time job for me. So let's turn off the Kraken. And we have all of these things ready to go. Can't quite build the real system yet. I want to get the mass storage devices ready to go, and then we will swing into looking at the CBIOS and hook it up so that it actually talks to these things. At that point, once we have operator interface and mass storage, then we just need to set up the mass storage to contain some programs, and we're golden. So I'll see you in the next one. Meanwhile, keep it small, keep it safe, and keep it fast.